file again now. Oh, I think it just saved itself. Yep. All right. Because I got autosave turned on, so I'm pretty sure we didn't lose too much. Let's double check. I don't trust myself. Neither should you. No. Deja vu. It's playing in full screen. I need to find out whether I can. Oh, there we go. Okay. Uh-oh, that's not good. It missed. So it would seem. Or not. I don't know. Let's open it again. Now it started from the beginning when I started to work on find prime, so I think it captured most of what we talked about, if not all. Pretty sure about that. Anyway, but that's why we have a trace. When you look at a trace, you should be able to figure that out anyway. I mean, instead of just talking about how the variables get changed, you now can actually go step by step and know exactly how they got changed. So are there any questions at this point? No questions? We have just enough time to write the binary search algorithm. Do you still remember binary search from last time? So let's go ahead and write that algorithm. Oh, that's the algorithm design part of this class. Is how do we start with something that we know how to do, and translate that into a programming language. So once again, we start with a really blank slate at this point. We'll just call it text.txt. Okay. Do you still remember the binary search algorithm from last time? Okay, yep. Question?
Search right in the middle and see if it's greater or lesser.
Correct. Let me pull up the spreadsheet from last time so that we can take a look at that. This spreadsheet is actually quite useful because it also illustrates, how I won, how I kept my job. You remember, I had a competition with Pat last time, and my old P3 won.
Is that a true story?
Hmm?
Is that a true story?
No. Okay, but this is binary search. Okay, it's based on comparing the middle element, and every time you compare, you toss away 1/2 of the array as possible candidates. So every time you compare, you reduce the number of candidates by 1/2 until you have one left. Then you still have one more comparison because it is possible that that one last element is what you're looking for. But when you have nothing left, then you can stop and say, oh, sorry, it's not a part of the array. So this is how we did it by hand. So now the question is, how do you write the pseudocode to encode the same logic so that you can have a computer to do it for you? Well, the first thing is, do you think it is somewhat repetitive? Are we doing something again and again? Yeah? At the outermost layer, are we doing something over and over again? Okay, so that means it is a loop of some kind. Now, since I don't know whether it should be a pre-checking loop or a post-checking loop, I'll just say that this is some kind of a loop. Okay? And that's my first revision. Just saying that it is a loop. Now, this is actually significant. Knowing that it is a loop means that in the next step, you have to say, oh, but when am I supposed to get out of the loop? And when should I stay in the loop? You have to ask that question next. And how do we answer that question? Loop and loop. Exit when? When do we get out? Let's not think about in terms of arrays and all kinds of technical stuff like that. This is a search algorithm, right? Just like linear search is binary search, but it is still a search algorithm. Yep.
It's a or thing. You either find it or it's not in there to be found. You either found it or you went through everything and
Very
you didn't
good.
find it. What's it called?
Okay, let me hear what you have to say.
Yeah, it's like if there's one match or none.
Okay, so
Left.
I can say, when a match is found or confirmed, or none of the elements match is. Okay. Now I have to be very specific here. I cannot just say, an element or the element does not match. Because if you have an array of 8 billion items, just confirming that one element does not match what you're looking for is not reason to get out of the loop. The only reason why you should get out of the loop is to confirm that none of the elements is matching what you're looking for. Is that okay? I mean, does everybody understand why I have to use this language specifically and not just say an element or this element does not match? And I'll just call this the next revision. Now, this is already important. From the first to the second revision, I have just added some really important logic to the loop to tell me when I can get out of the loop. Even though it's not expressed in arrays or comparisons or anything like that, it tells me what I'm supposed to do here already. Okay. So in the third revision, I should start to use some variable names. I will say let k be the value that I am looking for. Okay, because I don't want to just say the value I'm looking for, the value I'm looking for, the value I'm looking for. K is a whole lot easier to say and to refer to. Let A be the array that I am searching in that may contain the value. Okay. And then I can say let M. Okay, I can use I. Doesn't matter what variable name I use. Yep.
Sorry. Sign in.
Oh. Thank you. Thanks for the reminder. Here's the
And
sign-in sheet.
you skipped a word that may contain.
Oh, that may contain the value. Okay, so I need one more thing. I need some sort of index to control which element in the array I'm looking at. So let I be the index of the element that I am examining or looking at. Okay, so with these three names, I can now start to become a little bit more specific. And loop exit when. Okay, how do I say a match is confirmed?
K equals I.
K equals
AI.
A bracket I. Okay? Because I don't want to match this. This is not what I want. Because this is only matching. This is not. Okay, I know this is not what I want because nowhere in this expression is A mentioned. So how can I use this to confirm that what I'm looking for is actually in the array? I cannot. But this will do it. Because what this says is a particular element. I don't know how to find the I here, but I'm just saying that for some value in variable I can confirm this. And that's good enough for me to get out of the loop. I don't need to know how many items in the array would match the value of k. I just need to know at least one is matching the value of k. And that's good enough for me to get out of the loop. The second part, I don't know quite how to express it yet, so I'll just keep it the same way as before. None of the elements matches. Okay. Now, what I have at this point here can also be a prototype for the linear search algorithm, because you can see the logic applies the same way to linear search as well as to binary search. Except in the case of a linear search, I is initialized to 0 to begin with, and I keep going until I is no longer less than bar a bar. But in binary search, it takes a slightly different direction. In binary search, how do we compute I? Well, yep, go ahead.
1/2 of
The beginning and the end.
A total of A bar A, A bar A
Well, it's
bar?
not always that, because when you look at the example here, when you look at column B, then yes, it is exactly 1/2. But when you look at column C, it's not quite 1/2 of bar A bar, because you have to take into account that this time we're starting with here, starting at that point. In other words, the starting point and the ending point of the array that may contain the value that I'm looking for changes. Is everybody understanding that? Let me describe it more graphically here. In the first iteration, the entire range can potentially contain the element or the value that I'm looking for. Is that right? That's before the first comparison. The first comparison enables me to throw away about 1/2 of the array, and then I only have the second half to worry about. After the second comparison, I can throw away a good portion of the second half too, which means I only have 3 remaining to compare. After the third comparison, I have 1 element left. And then after the fourth comparison, I got nothing left. Is that okay? So what I'm actually trying to keep track of is which part of the array may contain the value that I'm looking for. Is that okay so far? Does everybody understand, what I'm saying here? Because I need a way to express that. But before I can find a way to express it using pseudocode, I have to be able to at least visualize it, using a spreadsheet. But what I'm really controlling is this. Okay, let me just do that again. At first, the entire array may contain the value that I'm looking at. And what is the index of the element that I'm actually examining?
2 to the prime of 4 minus 1.
It's 1 plus 15 divided by 2, and that's here. Right? Are we doing okay so far with that? The index of the element that I'm comparing to is the range, the beginning of the range, plus the end of the range divided by 2. Is that okay? Okay, now that I toss away the first half, I only have this much left. So the range of the indexes, I know, this is starting with 1 and not 0, but it doesn't matter, it still works. The range in this case starts with 9, ends with 15. 9 plus 15 is 24. 24 divided by 2 is 12. And which element am I comparing to? The element at index 12. Okay? Now that I can eliminate the other half, I only have 3 of these left. My range goes from 9 to 11. 9 plus 11 is 20. 20 divided by 2 is 10. And guess which element I'm comparing to? The element at index 10. Okay? So through this exercise, in my mind, I can say, if I can keep track of which part of the array may contain the value that I'm looking for, then I know how to compute the index of the element that I'm supposed to compare to. Is that fair? Okay. So back to the pseudocode, I'm going to say something like this. I'm going to invent new variables for that purpose. Let B be the index of the first element that may have the value. Okay. And then I'll use another variable E, B for begin and E for end, be the index of the last element that may have the value K. So I'm using 2 additional variables to keep track of the range in the array where the value that I'm looking for may be there. Okay, it's candidate to be searched. Okay. So with these, I can make my algorithm a little bit better now. Okay, because what I can do is I can say, oh, how am I supposed to compute I in this case? Well, you remember what I just did?
B, A of B.
You're going to assign I to B plus E divided by 2.
Exactly. Is that making any sense? So now that, as long as someone gives me, some reasonable B and another reasonable E, at least I can compute the index of the element that I'm supposed to compare to, because it's just the midpoint. Now, of course, in this case, for some magical reasons, I always turns out to be an integer. It never is. It's never a fractional number, and that has to do with me picking 2 to the power of something minus 1 as the number of elements. If I pick anything other than that, then there's always a potential that this number may be fractional. But that's an issue we can deal with easily later on. Okay. Well, but since we're talking about comparing that element, being equal to is one possible outcome, but there are always other outcomes. There are 2 possible outcomes too, in addition to equal to, because we can say what happens if k is less than a bracket I. Well, we'll think about that. What happens when k is greater than a bracket I? And I'll just throw this in at this point. We'll probably get rid of this later on. Let's just keep it here for now. Okay. What if k is less than a bracket I? And we have to understand that the array is sorted in a non-decreasing or increasing order. Okay, because this part depends on how we sort the array to begin with. But assuming the array is sorted in a non-decreasing order, what happens when k is less than a bracket I? In other words, the value that we are searching for is less than the one that I'm comparing to right now.
After you would eliminate all the elements that are greater than A. Right?
If k is greater than, you have to eliminate everything that's less than the element that you're comparing to.
Yeah, but it says k less than.
Oh, k is less than, sorry. I was looking at the line. I was looking at this line, but we're actually talking about that one. Sorry. So if k would, go ahead.
I was just going to say, the only thing we have to do is reassign the E index
Very
to
good.
reassign E to the index that we're at, and then run through the loop.
So let's find out how we're supposed to change the ending, because what it means when k is already less than a bracket I is to say that k is also less than a bracket I plus 1 close bracket, because everything after a bracket I can only be as big as a bracket I, and all of those will be greater than k already. So we can eliminate everything that's after that. So how should I change E?
E gets a bracket I.
Well, what about this? Would that be okay?
Yep.
Well, is a bracket I, can a bracket I match k? That's the question. Nope. Since that cannot match k, we have to do it like this. Okay. Does everybody understand why the -1 is so important here? Because without the -1, we are still saying, oh, a bracket I may match the value k, but that's not the case anymore. So you have to move it one element before the one that you actually compare to in order to reestablish the new ending of the range. Well, that means this one is going to affect B. So how do we change B in this case?
I plus 1.
I plus 1. Very good. Remember, the plus 1 is just as important for the same reason here. What if they are the same? Is there anything I have to do inside this conditional statement when they are exactly the same?
No.
Nope. There's nothing to do. If you want to say woohoo, that's fine too. But there's no need. So there's actually nothing to do. Okay. There's nothing to do because you cannot say else if A equals a bracket I, then get out of the loop. Because inside the loop, you cannot say, I want to get out of the loop. You have to wait until you get to the end of the loop. When you specify the exit condition, that's when you can say, oh, that's a reason to get out of the loop. Are we doing okay so far? At some point, you will learn another taboo word. Remember the G word? Go to. At some point, you will learn, 2 other taboo words in programming. One is the B word called break, and one is called the C word for continue. There are different ways to, one will get out of the loop, the other one will go back to the beginning of a loop from anywhere inside the loop. Those are also taboo words because if you use those constructs, then you can no longer, it's difficult to track the logic of your program at that point. Okay, so remember that. All right. Now, let's see if we can take another stab at this statement here. None of the elements matches. Is there a way to say that now that we have these additional stuff to remember the range of the array that may still have a value that may still contain the value that we are looking for? Yep.
When E equals B but does not equal K?
No, does not involve K anymore. Let's think about this. Okay, if you just kind of visually imagine B started off all the way at the beginning, when we first start the algorithm. E started all the way to the end. After one comparison, what happens? Either this one moves to the center, or this one moves to the center, right? And then the second step, the same thing. Either this one moves over here, or this one moves over here. So with every single comparison, B and E, they get closer and closer, right? At some point, they can become exactly the same, just like in this example here. At some point, only this element is the only one left. But what happens after that?
Plus keys.
Okay, they go like this. Okay, at some point they become the same. Now, after they become the same, let's look at the algorithm and see what it means when they are the same. In the algorithm, when B and E, hold on a sec. When B and E are exactly the same, then B plus E is just 2B or 2E. They are exactly the same. And I becomes the same as B or E. In other words, when you only have one element left, then I, B, and E are all the same. But the logic still goes. It still looks for K being smaller or K is being larger. So that means at some point, E will become I minus 1. But remember, B is the same as I. So that means E will actually become less than B. E may become less than B, or B will become E plus 1, the same thing. B is now greater than E. And that makes no sense because by definition, B is the beginning of the range that may contain the element that you're looking for. E, by definition, is the end. What happens when the beginning is greater than the end? That means there are no elements left in the array that may contain the value that you're looking for. So we are looking for that condition as our indication that none of the elements matches, because that's exactly when this happens. When B is greater than E, then you know there's nothing left in the array that can potentially be a match for K. Because B starts from the beginning, E starts from the end, and they should always maintain that relationship of B should be less than or equal to E. They can still be equal to, but not overlap. And we're just going to go a little bit over time this time. We'll go through the initialization. How should I initialize B? How can I say everything in the array may contain K initially? What is the index of the very first element? 0. What is the index of the very last element?
RA bar minus 1.
RA bar minus 1. Very good. And then we have the loop here. Should this be a pre-checking loop or post-checking loop, or it doesn't really matter? Let's think about it. Where does I come from? When is the first time I initialize the value of I? It's inside the loop. So that means I cannot turn this into a pre-checking loop. So we turn it into a post-checking loop using repeat until. The nice thing about until is you can keep the same condition because we have been specifying the exit condition from the beginning. And now we have the binary search algorithm. Any questions? Yep.
We're not going to have to do this on the test, right?
No, you will not be required to write new algorithms. But I'm illustrating the process that I go through in my mind when I write the algorithm, and emphasize that the fact that we cannot just start from line 1 and just keep going like this. You have to go from the structure. You have to base on the structure of the code and start adding more logic, more details each time. I'll see you guys on Thursday.
Can you go down just a little bit?
Go down to
Where you were initializing? Oh, there it is, right there.
Save.
save. Yes. No. Have you checked?
I checked on e-services.
And you just do not on the list?
Yeah, it's still on.
Okay. I have to talk to the dean then.
I'm not saying
Okay. It's better if you talk to the dean.
There's left a lot more now.
Yeah, I put your application onto his in file, so he should have seen it already.
So I just go to the office and
No, the dean's office is over there. You know,
What's
it's
that?
in
No
room
good.
133.
Yeah,
33? All right.
unfortunately. My family
Questions?
doesn't know normalcy.
Thursday.